Nej, precis. Men man får ju liksom Ja, men verkligen. Så man känns som att man ska större.
Okay, welcome everyone to the RMCAT session. So I'm Anna Brunström, and next to me is Colin Perkins. We're two of the co-chairs. We also have Martin Stimmeling. He's not here in Singapore. Probably also not online, given the time zone, yes. The note well applies, of course, as always. You can find all the meeting material on the usual slot. Do we have, we need a minute taker? And the jabber scribe. Thank you, Jonathan. Do we have a minute taker as well?
So I will take notes, but it would be useful if someone else could take some as well and send them to us to cover any gaps.
Yeah, our normal note taker is not here. Okay, can anyone help Colin out a bit on the notes?
Gori, I'll help you out, but I've got to first type an email to Quick, which is going to take like 10 minutes to type.
I'm sure nothing important will happen in the first 10 minutes.
Thank you, Gori. Okay, you have seen the agenda. We've been through the administrative part. So as normal, we'll start with the run through of the working group status on the different documents. We then have Xiaojing, who will present the updates to NADA. This will be a remote presentation. Ingmar will show some of the experimental results with Scream. And then Sahid will give us an update on the design team's work on the feedback message. For the working group document status, so we now have 2 of our candidate algorithms that are in the RFC editor's queue. So the coupled congestion control is there waiting for the NADA draft because there is a normative reference. So once NADA is completed, the coupled CC will proceed. So that is ready. The Scream draft is also in the RFC editor queue. The shared bottleneck detection, the write-up for that draft is ready. So during that review, there were a few nits that David will fix. So we expect to ship that next week. The NADA draft got a number of comments during the working group last call. So we had an update of that following that feedback. And Xiaojing will present the updates and new evaluation results as part of this meeting. And for the Google congestion control, that draft is still pending author updates. So I guess we will have to see what will happen with that one. For requirements evaluation, we have the old requirements draft, which is still in the editor queue, waiting for other documents. Then we have the evaluation drafts. So we have the pair there, the eval test draft that is ready for working group last call. What is holding that up was that we wanted to ship it together with the eval criteria. And here we are waiting for a small update on the TCP model. So that draft has been stalled in that status for a bit. So we're trying to push the authors to get that in. And if not, we may have to have another approach to move the documents forward. So I think Varun was saying he was hoping to put an update of it this week. So we will see what happens. Otherwise, I think we have to put the deadline for that draft and maybe see if we can get another editor in to help complete them. So I think it would still be useful to have them go together because they are so tightly coupled. But it's a small update that is missing one of them, and the status has been the same for quite some while there. So we would like to get those documents moving. Then we have the wireless test drafts and the video traffic model. And those documents are also basically ready. I think maybe Xiaojing will also say something about the video traffic model today. So we need some reviews and implementation experience. So we discussed all of these drafts the last time. The feedback draft has now been moved over to AVT Core. So Sahid will report on the completion of that draft here. Then we have Colin's draft on the analysis of the feedback. So that draft will remain in RMCAT and I guess be updated depending on what happens with the other draft to follow as a supporting document. Then we had the different drafts related to the interfaces, and we had that up for discussion in our last meeting. And the conclusion was basically that we thought that the codec interaction, or the working group thought that the codec interaction and the framework draft could still be useful. And Varun and Sahid had an action point to try and go through these drafts and come back to the working group on the suggestion on how to proceed.
Hi, Jahad. On the framework draft, there was a comment that this need to be in line with the RTP topology draft, RFC right now. I have reviewed that again, framework draft as a co-author, and I didn't really find that there is so much need to be updated on that one. The question here is more about like how do you align the codec, CC codec interaction with RM framework draft. My opinion is like, yeah, it's just like putting them, I mean, figure it out, like basically it's a 1 draft or 2 draft we need to be. Having said that, I think me and Varun, I kind of we didn't manage to have a time to actually do that, but I hope we can do it faster. But otherwise, the framework draft, especially, I think, is pretty good shape actually.
Okay,
Can I say something? Do I need to get in the queue? Sorry.
No, please
Oh,
go
that's
ahead.
okay. Yeah, thank you. So for the framework draft, maybe one thing I should mention is that we're open sourcing the NS3 RMCAT code, and that code kind of provides a reference implementation of, let's say, our understanding of the framework. So it can sort of serve as a reference as well. Yeah, and as Zahi was mentioned, the previous comment on aligning the terminology, that's something we can address, but it's more finding the time to do it. Yeah. Thank you.
Okay, thank you, Shashing. But so Said, you and Varun will still have a look at both of the documents and come back to the mailing list as we discussed last time, or you're now suggesting another approach forward?
Well, I cannot speak for Varun, but it has been, I mean, lack of time basically. I mean, my approach would be like, well, if it is important CC interaction, if the framework document is really is ready and we have a reference implementation for that one, then perhaps we should deal with them separately. Framework document, I mean, as one of the things that pointed out in previous meetings, like none of the candidate algorithm currently follows the framework document, but this was the I think the reasoning here is like when you will go on a standard track, then framework document will be used and stuff like that. Maybe we should deal it separately, because and I'm not actually sure right now like how much CC codec and framework document need to be, I mean, aligned. I'm not sure about it, but Varun has more strong opinion than me, so maybe it's better like I can talk with Varun. Let me put it like that. I'll talk with Varun and see like what he thinks about that one, and then update the working group on the mailing list. Sounds good?
Okay, yep, sounds good. And as you said, say the current drafts do not follow the framework, so will come in the next step, hopefully for this. So in that sense, it's also not extremely critical at this time, because we are not on this point. So, but it would be good to have a plan for how we proceed with them. So, yep, that sounds good. Okay, so our milestones. So we have now completed a few of the ones that we had in the summer. So we have the coupled congestion control was shipped just before our previous meeting. So that completes that milestone, or at least partly, and with the SPD draft being hopefully sent next week, that milestone will be fully completed. The congestion control candidates, the first ones with Scream, has been sent, and feedback requirements sent to AVT Core has also been completed. So the one that we are a little bit behind with now, that is the requirements and evaluation draft. So maybe we'll update that and say, but we should try to get that out. So we will see how we will put the deadline on the updates, and then look for other ways to proceed if it cannot be done.
Yeah, I think that's the right way to do it. Put it on our deadline. Like, well, we need to fix it before that one, because the other draft, the test drafts are waiting on it. So I don't see any reason for doing that actually.
Yep. Okay, and then we have our the rest of the deadlines is coming later next year. So, okay, do we have any questions or comments on the status? If not, we proceed to the presentations, and Xiaojing is first up with the NADA draft. So Xiaojing, will you also be able to control the slides from your side, or you want me to display them here?
I don't yet see the control for the slides. Yeah, maybe it's easier if you flip through them. Yeah. Yeah, the chair, yeah, I also got the note. The chair needs to control them.
Okay, you're a little bit loud, Xiaojing. If you can turn your
Okay.
volume.
I'll try to speak more softly.
Thank you. No, that's good.
Okay, good. We're ready for you.
Yeah, great. So yeah, I'll give an update on the NADA draft. Basically, actually, the next page gives a brief outline. So basically, the updates are several aspects. We have some update on still, tweaking the algorithms, but mainly isolated for the loss-based behavior and sort of scenario alone. And then accompanying the draft and the algorithm design, there's the open source code. So I'll give a status update on the open source code for the NS3-RMCAT. That's where the NADA reference implementation is. And I'll also mention briefly some update on the sync codecs open source code, which is more tied to the video traffic model draft, as the chairs have mentioned. We do have a slide to cover that. And finally, with these updates, I'll show some sort of a selection of updated evaluation results. We have the 4 set ready to be shared with the mailing, sort of the mailing group, working group. But I didn't want to bore you guys, to flip through 50 slides. So I picked a few where the changes are reflected in those sort of more representative ones. And finally, a summary of the draft changes from 04 to 05, and also some of the, I would say, planned changes for another revision, just because of some more recent review comments we have received over the mailing list. Next page, please. Basically, for the algorithm updates, we have been motivated by actually the issue reported by Julius Flor from on the mailing list. He reported the problems he encountered with his own Omnet++ implementation of the NADA algorithm, and he basically reported that for low link scenarios, NADA seems to be pushing away other loss-based TCP flows. So that was kind of motivated us to revisit that part of the algorithm and hopefully do a better job of coming up with a more robust behavior when it's competing against other loss-based flows. So the changes we made in the algorithm are actually kind of revisited the entire flow, in the sense that we tweaked our decision in whether to get in and out of a loss-based mode. Basically, we adopted a self-adapting thresholding to make it more adaptive, so that it can sort of self-scale for different link capacities. Then secondly, for this transition, also, this is more like a technical tweak. We also added a linear interpolation when our algorithm is getting in and out of loss-based, basically switching between one mode in another, because the way the congestion signal being calculated is following 2 different sets of equations. So in between, when we're doing the mode selection, we just added a linear interpolation to ensure a more smooth transition of the reported congestion signals. That gives a more, basically, that avoids some of the radical changes in the algorithm, sort of in the sender adaptation. And then finally, in our loss penalty function, in previous versions, we've been following a linear sort of a mapping between observed packet loss ratio and a corresponding delay penalty term. In this version, we have changed to a quadratic after some experimentation. We find a quadratic form, a mapping between loss and corresponding delay penalty, tends to kind of penalize, hold back the NADA flows at lower link rate. That was also basically motivated to make NADA work at lower link rates, not to starve other flows. So these are the main changes. Next slide. I'm going to maybe explain a little bit more for this self-adapting thresholding part. Basically, in the previous version of the draft, we simply picked kind of an expiration date. It's kind of a expiration time. It's a fixed threshold to consider whether the flow has observed losses, and if the flow no longer observes losses within a given period of time, it will try to get out of the loss-based mode. That obviously needs to be tuned for different link capacity environments, because TCP sawtooths will have different widths for different delay and bandwidth products. So in draft 05, we actually adopted the calculation used by TFRC for calculating an average loss event interval. And we use that as the basis for coming up with a threshold that now self-adapts with this measured average loss interval. So this makes the algorithm a little bit more self-scaling, as we will see in the results. And then, of course, to be a bit more tolerant for missing a loss event or two, we add a constant multiplier. So there's still a parameter to be tuned, but it's much less sensitive. Typically, we can stay with the same constant multiplier, and it will work with a wide range of bottleneck link bandwidth. To illustrate this, on the next slide, basically I'm showing the experiment of test case 5.6 in the RMCAT eval test draft, but then by changing the bottleneck capacity. So on the left, you see the result where NADA, the blue flow, is competing against TCP, the purple, at a shared bottleneck of 1 meg. And on the right, they share a bottleneck of 10 megabit per second. So the rate TCP gets, it's out of range for this plot. But what we want to show here is that in both cases, during the middle part of this experiment, where TCP starts, NADA sort of correctly operates in loss-based mode, even though the TCP sawtooth behavior, the width of the TCP, sort of is widely different between these two. So this is an illustration of how the self-scaling helped us to, for the algorithm to correctly switch between the mode without having to hand tune them for different environments. Next page. And then this is more a summary. So for test case 5.6, and we really want to ensure that it's kind of robust for a wide range of environments. So we followed actually kind of I would say like the suggestion or the exercise that Julia was doing himself, basically by sweeping over different bottleneck bandwidths and different propagation delay values. And here we report the average rate the NADA flow obtains when competing against a loss-based TCP under these varying parameters. So there are two regimes. On the low bandwidth case, let's say below 2 megabits per second, we can see that regardless of the past propagation delay, in this updated version of NADA, we share the bandwidth with TCP roughly equally. Basically, we're getting approximately half of the bandwidth. Now, when we get to the high bandwidth case, ideally, that's where the total link bandwidth could have accommodated NADA flow at, sort of max rate without backing off at all, and then, TCP on top of it. But because NADA is still reacting to losses as a measure of congestion signal, ever so slightly, so it still backs off very occasionally, as you guys have seen in the previous graph. So we don't get to operate at our max. And also because of the sawtooth widths, basically different link propagation delay would exert different amount of penalty, I would say, on the NADA flow. But still, maybe the message taken back is that we still can hold some ground. And obviously, in this case, we're no longer starving TCP. So that's the main kind of study we did for improving the robustness behavior of NADA in the loss flow competition environment. Next page. Now, the other thing we changed in terms of our evaluation approach for the codec is for the NADA congestion controller is somewhat tied to the traffic source we use for driving it. Previously, all our experiments are reported mainly based on this, what we call the perfect, but basically it's like mimicking CBR behavior codec. But then when experimenting with this TCP-based flow, we realized that with the video codec behavior, one main thing is that for a given fixed frame per second, sort of for a given frame interval, at least the flow has some presence, on a periodic basis. So we added a new traffic source type in our implementation of the sync codecs. That's more tied to the video traffic model draft, where instead of spreading out, let's say at very low rate, instead of having a very wide packet interval, in this case, we actually still have a fixed frame interval, and also based on the video traffic sort of data analysis we presented previously at IETF meetings, we added some random perturbations of the frame intervals. So we believe this new so-called fixed FPS codec is a somewhat more realistic, sort of modeling of the video traffic behavior. So for all our test case evaluations, as you will see later, we use this one as default. But of course, our implementation easily supports switching between different codecs. The other one we added is this hybrid codec, which most of the explanations are in the video traffic model, where basically we combine the trace collected from realistic encoding experiments with some statistical modeling of the transient behavior. So that's another one that updated the current video traffic model has already described, and now in our sync codecs implementation, we're just catching up. So let me just insert a brief status update, right, for the traffic model draft. Basically, as to our understanding, there's no more sort of outstanding issues or sort of to-dos that we want. I think we have basically completed all the things we have thought of and wanted to control. So that draft should be ready for further review and maybe working group last call. I don't know. Yeah, but we're actually not getting enough review, and the code is of course available online. And next page. So now getting back to the other open source code, that's the NS3-RMCAT code. We have presented its structure and how to use it kind of more in a forecast manner in our last interim meeting. And now, finally, we're happy to report that we're ready to release the code. I just checked the link before joining the presentation. My colleague Sergio has already sort of released the code. So the link, it's not really soon, right? It's online available now. Yeah, so we really welcome people to take a look at the code, and it's basically implemented as a standard NS3 modular and somewhat follows the conventions of NS3 submodulars, and also it adopts the sync codecs as the traffic source using sort of the submodular import mechanism, and it supports reference congestion control implementations. We have provided 2 examples: a dummy controller where you can configure, the sending rate sort of explicitly, and whatever you configure, the controller just send at that rate, and you can change on the fly. And another controller, which more or less follows our draft description up to version 05, literally. So, and then of course, hopefully with these 2 controllers, you guys can get the idea and do your own controller. We have designed the code so that we think it should be easy to add and try out your own, and we encourage people to give us feedback on that. And then also in this reference implementation, we have support for the test case, both the wired test cases and the Wi-Fi test cases. That's the section 4 in the wireless test case. The missing part is cellular, and we need some additional support on that. There's a question. Should I take it now? Yeah.
Yeah, Jonathan. So does your simulator use this the feedback as specified in CC feedback, or is it still using one packet per feedback message? Because I know there was some.
A great question, because while we were developing the code, the feedback messaging draft is still kind of evolving. So we're basically using the basic per packet feedback, but we have already embedded a to-do to catch up on the draft. Yeah. So the next page, yeah. Now I just flip through, maybe bear with me with a few slides of update on the results. This one is to show the test case 5.1. That's, where we first tried our case. And I just want to show how it works for different traffic sources, the CBR and the fixed FPS. That's the new default that we adopt for all our evaluations. As you guys can see, it more or less follows the same behavior, but there's a little bit of noise or variation because of the frame interval perturbation we have added. Yeah, so the name is a little bit misleading. It's not fixed, it's really fixed with perturbation. Next page. And then these are the behaviors when we have the hybrid codec, where the frame sizes are using in sort of recordings of encoded frame sizes. So sometimes, the codec output is lower than what's specified. And then the one on the right is for content sharing, which is, there was some discussion, I think, early on, previously on the mailing list, which attempts to mimic the behavior of slide sharing behavior. So occasionally there's a big frame. Otherwise, the frame sizes are very small. Next page. And this is the case where I'm showing the kind of the before and after for the test case 5.2. As we reported in the previous meeting, so previously our loss-based behavior was still fairly fragile. So in this case, it actually got locked in the loss-based mode. But after our kind of somewhat tweaking of the loss-based behavior, we now got a better result, for that part of the graph. And then everywhere else, you just see a bit more sort of random fluctuation on the sending and receiving rate. Next page. So the other one that at least personally I always want to check is this case about round trip time fairness. So as you can see in this new version, we still converge to the same rate regardless of the different propagation delay each flow experiences. And but then the flip side is that the sending rates are not as smooth as before, because now we have this fixed FPS traffic source. And it takes also even a bit longer to converge. Next one. So that's kind of all the evaluations results I'd like to share during the presentation. I'll be happy to send maybe a PDF document on the mailing list for maybe a link to the full collection of results for people to review. And to summarize the draft changes from 04 to 05, that's the change we have already made. The main changes are really in updating the algorithm descriptions as as I just explained for the loss-based behavior. And I believe that one have also addressed some of the review comments we have got from working group last call reviews. And going forward, we have more recently collect some additional review comments from Roland, and also Michael has pointed out some kind of mistakes in our use of normative versus informative references. So we basically intend to collect additional issues that we're aware of, basically update and fix those, and also update the section 7 now implementation status. Just want to check if my audio is fine, because I think my slide is gone. My slides are gone. Can the room hear me correctly? Oh, great. Yeah, so somehow I can't see the slides. Okay. If the people in the room can still see the slides, I have a local copy, so I can keep talking if you don't mind. Basically, for the draft, yeah, so these are the things we plan to update pretty soon, probably, let's say even, during the course of IETF 100, we can update the draft because these are things we already have information on. Oh, yes. Okay, can you guys hear me? I hear
yes.
some.
We hear you.
Great. Yes.
But
I don't see this. Okay, great. So the slides is back. It's a it's a live test, and like all live systems, it had the sorry for the glitch in between. Yeah, basically I was trying to mention that for our planned changes, all these we can complete fairly quickly because these are things we already have sufficient information on. Maybe my question back is like what happens, let's say, after we submit 06, that I'm expecting, let's say, by the end of this week, we should be able to update. Of course, we want people to review the updated changes, but maybe process-wise, do we need to go through this working group last call again, or is it more that we can rely on the reviewers who have provided feedback before to kind of double-check the changes we have made? And then assuming the draft goes well, but sort of working in parallel now, what we want to do sort of as a next step is to start thinking about real-world experiments, sort of moving beyond simulation. And we've previously have collaborated with Randall a little bit and got his help in trying out NADA in Mozilla browsers, but we kind of dropped that thread, due to time constraints. Now we feel like since the simulated version, the code is out, we can come back and look at experiments. So that's what we want to focus on, sort of experimenting with embedding NADA in the Mozilla open source browsers. Yeah. That should be the end of my slides, I think. Yeah. In the backup, I have a few additional results, but that's more like if people ask to see specific things.
Okay, thank you, Xiaoqing. So regarding the process, so as you have now made some updates to the algorithm, we will run a second working group last call on the draft, and that in parallel, of course, during the previous reviewers also can check that they are happy with the update.
Okay, sounds great. Yeah.
Do we have any questions or comments for Xiaoqing?
Ingemar Johansson. One question about this loss-based behavior. Did you evaluate it with this CBR-like model, or was it with this more real video model?
Well, not the real, the fixed FPS. So in our simulation, for instance, for test case 5.2, we have also tried out the CBR-based, and I take it back. Actually, not for 5.2. For 5.6, in our simulation, we can also turn on those other traffic sources. But if I remember correctly, we didn't get satisfactory results early on. But then after we tweaked the algorithm, we didn't revisit it as much. Yeah. If you're asking about CBR-based behavior. Yeah.
Okay, thanks.
Jonathan Lennox, I guess sort of related to my previous question, you guys, in your plans for experimenting in the Mozilla browsers, are you planning to implement CC feedback there, or is there some other? I know they have various other preliminary mechanisms. What are you planning to use for the feedback when you're in Mozilla experiment, or do you not know yet?
My understanding is that basically for our algorithm to work, we kind of need per packet information, right? So at least at the receiver, we need per packet observation of the delay and packet loss. We may need to look into whether the current feedback mechanism already supports it, or maybe we need to add some receiver-based operations. Yeah.
So, yeah, I suspect what you'll need is, in fact, CC feedback, which will also be useful for testing whether CC feedback is actually workable.
Yeah, I think that would be really good. And Xiaoqing, it would also be great if you send the link to the full set of experiments that you have performed. Okay. Then the working group also has access to that when we do the second round of working group last call.
Sure. Yeah, I'll probably send out a link, sort of like a Dropbox link, so that I don't, flood everyone's mailbox. Yeah, with a big file.
Yes. Just so it's accessible. Okay, thank you, Shashing.
Thank you.
Then next up is Ingmar.
Spicy food. Okay. Okay. Do it like this. And there's also a presentation of some Scream experiments with a sort of an application that is outside the original intent of this RMCAT working group. And it's using it to remote control vehicles. And on the picture you can see Robert and Olof, students at university, Luleå University of Technology, that sort of just took this Scream multi-camera and that's the control software and put it on a permaball chassis with all the remote control. They had a lot of fun with it, and the intention is that in the long run it will end up in a mining truck. So it's some serious matters around it, not just fun. And yeah, we can take the next slide. And unless I guess everybody knows what it is about. It's about going from a crappy video image when you want to remote control a car or something for whatever you want to do, a reason you want to do it, to get something that is more stable. For instance, somewhere around here on the left pane, you should see a car that's sort of turning out and around. If you use congestion control, you all of a sudden see the car and you can hit the brakes so you don't hit it. And what is not visible is that it's on the left-hand side, you had almost 1 second delay in the video. And okay, we can then next slide. And the problem is that if you want to do remote control and you want to have a remote control user that doesn't get exhausted after one half hour or so, you need to have very good quality. And that is for the ergonomics. And you need to have several cameras in order to get sort of a almost like driving experience. And high contrast video is important also. And all of that results in peak bit rates that can excess 30 megabits. And even though we boast that LTE and 5G deployments can guarantee high uplink bit rate, the reality is sometimes you end up in congested cells or bad coverage or a combination of the two. So any sort of remote control operation needs to be rate adaptive. That's quite obvious. And you can do some enhancements to improve the performance. You can densify the network. And that is sort of an ongoing process all the time. And you can add quality of service. You can prioritize. If you want to sort of a commercial application, you can prioritize, use another bearer with higher priority for your remote control applications. And also add explicit congestion notification to it all to avoid packet loss as a congestion signal and get ECN marks instead. But the thing that I'm going to present is without the two lower bullets, no QoS and no ECN. Can take the next slide. And what it looks like if you have a remote control and don't do any congestion control is that just get the camera feeds from the left-hand side from the remote entity and just fire and forget it, RTP or UDP. And whatever sort of bit rate that is too much will be queued up in the network or dropped in the network. And you can get queue and delay in over 1 second in LTE uplink before you get lots of packet losses. So it's not very useful. And in the best of cases, it works, but when it doesn't work, you don't want to drive the car. Okay, you can take next slide. And what you do is that you add a congestion control on the sender side, and you have some sort of feedback on the receiver side. That was in this case, it's a Scream, and it takes all the RTP packets and it sort of feeds back sort of bit rate information back to the encoders, and also you can have some sensor data of different kinds that you use. And you try the network congestion control tries to keep the network queue low, and that's good for interactive control and sort of avoid running over an elderly lady. And it's implemented in running code and using sort of off-the-shelf cameras. So you can take the next slide here. And if you take Scream in one page, I believe all of you have followed it, so it should be fairly familiar with it. And it stands for Self-Clocked Rate Adaptation for Multimedia. And it's a window-based congestion control, and pretty much like TCP, but without the retransmissions. If you want to do retransmissions, then you use the normal RTP retransmission mechanisms. And it acts on packet loss as well as delay, and also VCN is enabled in the network. And what you do is that you can queue the RTP packets can be temporarily queued up in the sender. So you don't send more data than is actually sort of act in the network. And that can mean that can have some queuing delay on the sender side as well. Developed since 2014, and it's actually now, lo and behold, is in RFC editor's queue after a long wait. And it has been a long run, but it's a long journey, but it's soon finished. You can congestion control most of the media that is packed in RTP. It can be video, audio, haptics, motion JPEG, and sort of this still image and all the stuff. But it's mostly only the video that is tested that much and sort of tried out. Multi-stream handling and prioritization, you can hook up several sort of cameras or sensors or that stuff, and you can sort of prioritize one or the other. The prioritization works so it's not an exact prioritization, and we'll show some more about that. Available as open source. It can operate between bottleneck speeds, so like 50 kilobit per second up to, and it has been tried up to 100 megabit. But the 100 megabit is what with fake video coders, because we don't have any video coders that produce 100 megabit video right now. Ongoing work, we're currently working on L4S support, and almost done, and will be pushed up to the GitHub when it's done. And there will be started a student project that will integrate Scream in a GStreamer plugin. Okay, next. The feedback is not the sort of the proper feedback format. It's sort of a homegrown feedback based on XR, and it has sort of it calculates accumulated size of ECN marked bytes and adds some an ACK vector and a timestamp. But all of this can be replaced with this AVT core CC feedback message when it gets more mature, which is, I believe, fairly soon. And also add support for bundling if more than one stream. If you have many streams now, you can send one RTCP feedback for each stream, and that costs a bit overhead. Can save some RTCP overhead if you bundle RTCP packets. Yeah. And the most challenging work has actually not been the network congestion part. That if I was allowed to sort of count the number of hours that's spent with this, sort of roughly 80% has been to cope with the varying bitrate from video coders. You have keyframes, you have large bitrate variations, and also there's a case that often the quantizers, they change on keyframe intervals. So if you're in the middle of a group of pictures want to change the bitrate, it's not a guarantee that the bitrate will go down or up. And often hardware video coders or IP cameras, they have very limited tuning capabilities. And that has had a large impact on the design of the congestion control. It needs to have additional checks and balances in the code. That is not necessary if you have sort of an ideal video coder, but reality sort of forces to add extra code to cope with that. Can take the next slide. And on the sender side, here we use sort of IP cameras of a Panasonic brand, and in order to make them stream RTP, you actually implement an RTSP client for each camera, and you sort of start the RTP stream and make it go through the stream sender where everything is multiplexed. There's some question on that.
Okay, Randall, you're up for a question.
One quick question on the graph on the previous slide. I take it you're running the video encoders with fixed interval iframes, and I would presume also that's because you're not handling error recovery via other mechanisms like retransmit and so forth. Is that true?
Yeah, there's no error recovery or nothing at all, because it's an IP camera. You actually can't request sort of RTP retransmissions. I don't remember RTX.
Okay. And of course, RMCAT's supposed to work for streams that aren't necessarily WebRTC streams, so some of those will certainly be non-error recovered.
Mm. Yep. Okay. And yeah, the congestion. Sorry, always talk about congestion and so on. Well, the complexity is quite modest. Currently, it runs on a Raspberry Pi 3, and it consumes like 5 to 10% sort of a CPU power. I don't have the exact figures because the Raspberry Pi implemented sort of a VPN tunnel as well. So, and it was below 20% when you're running at higher bitrate. So. I had the students doing that work for me. So, okay, and we can take the next slide. On the receiver side, you sort of demultiplex the streamers and play out on different sort of G-streamer play out. So that's about, and the player side is quite low complexity. So on the stream receiver is sort of dump on dump. It's only records received packets and create a feedback. So, and as regards to stream prioritization, and the objective is to ensure that if you have an important forward camera, for instance, you ensure that that camera gets the largest share of a congested bottleneck. If you don't have a congestion, then all the cameras will get a high bit rate. But it's only when the bandwidth starts to become limited that you sort of prioritize between. And it's something that's called weighted credit-based scheduling with configurable weights, and you will probably call it something else. So, and that alone doesn't help, but you need to also sort of enforce with priority rate adjustments to make it work. And that is because you have video coders that you cope with. And sometimes some given video coder is idle, even though if you're running with a sort of remote control permobile, and you can have a very low activity in one camera. It could be facing just a blank wall or something like that. And in theory, with this kind of setting on priority, the front camera would get 72% of a congested bottleneck, and the rear camera will 14%, and left and right we get a much lower share. But that is in theory, and the next page, I believe, shows what it looks like in a real test drive. And you can see that on the upper sort of a graph, you can see that the average bit rate is something, it peaks up to like 25 megabit per second. And you can see that the front camera very, very quickly it grabs the highest share of the bandwidth, and the other cameras pick up slowly as it sees that the bandwidth is increasing. And what can say more that between roughly 380 seconds and 420, we're running in a basement, so with very poor LTE coverage there. And you can see that you can get large delays when the link throughput drops, and that is not much to do about it. And one reason why you get it is that it's only delay-based congestion control. I had to turn off actually the loss-based part because they have some mysterious uplink packet losses, even though it's LTE. It shouldn't be packet losses actually, but it seems like obviously there's some kind of a very narrow sort of a shallow queue in the uplink processing that drops packets, because you don't see that much of a queuing delay, but you still have packet losses. So it's only delay based, and ECN would be really good. That is very high on my wish list. Preferably before I'm retired. And just joking, isn't it? Not quite a joke, but very close. And in some cases, could be that the congestion window doesn't react quickly enough to the increased delay, and this could be a setting issue of this delay-based sensing. And you can see that actually the prioritization, it works fairly well, but I believe it's not reasonable to assume that you can exact priorities, and I believe for that purpose, these 4 priority levels, I believe it's good enough. You can't expect in reality to get much higher granularity than that. That is my impression, at least. Next slide. How much time have I spent? Okay. The initial impressions of this stream prioritization and the average behavior in general it looks quite okay. In some cases, you have some glitches in the video, but if the benefit is actually when you have many cameras, if you end up in poor coverage all of a sudden, is that the lower priority camera will take the hit because of the weighted scheduling. So even though you sort of get a dramatically reduced throughput, the front camera will work quite well. So, and you get some kind of tunnel vision effect with the throughput drops, especially when you're driving in the basement. The side cameras were just crap, and that could be and some room for improvement. And is that to switch off some cameras in very problematic conditions. Add some extra code to sort of turn them off or just disable these streams, and also verify this runtime priority switch. And there is an extra sort of mechanism you can sort of in runtime you can switch. If you, for instance, want to reverse your vehicle, then you might want to increase the priority for the back camera. That is implemented but not tried out. So in no real media, only in simulators. Next slide here. And ECN support, yes, ECN works. Unless you're no shit, Sherlock.
What LTE carrier? What LTE is this actually in the LTE carrier is doing ECN for you, or is
no? LTE is still lacking ECN support.
Okay, so where is the bottleneck that ECN is doing something useful for you?
Where
is the bottleneck that it's giving you useful ECN signals? Who's doing the marking in this case?
You still have your sort of educational, especially actually in 3GPP. You need to educate and sort of convince that is good enough. In this setup, it's a fixed bottleneck actually running. And the upper graphs are simulations. And the one is without AQM, and the right-hand side is a Codel with ECN. And you can see that if you implement ECN, you get more stable sort of queuing delay and actually more stable bitrate. And this is sort of the mimics sort of keyframes also. It's a rather complex video source. And if you're there, you can look at the YouTube clips where I sort of run the Scream algorithm with IP camera and just waving with my hands and with and without ECN enabled Codel. And in that case, it was a 3 megabit bottleneck. And I mean, yes, that if you have complex video sources, ECN can improve performance greatly. So
can I ask, so this was an emulated scenario, but the one before was the real test?
Yeah, this is sort of an emulated bottleneck. That's correct.
But on your previous graphs,
that was a real test, but without ECN support, of course. So, okay, I have a question here.
Can I?
Yes.
Sorry. Yeah. Can you hear me? So actually, my question is regarding both for the ECN based one and for the previous one. When you're saying that the congestion window sometimes doesn't back up in time. What are the corresponding packet loss rates that you observe? Because the plots don't really report those. The flows experience, sort of packet losses. Yeah.
You mean in this one? You actually have packet
Yes.
losses in this case. On this slide, what is it, 12 or? The slide
Okay.
with-
So for ECM, basically, you're saying then what's the marking ratio? Yeah.
Yeah, and in this live test, there was no ECN capability in the network. Yeah.
Yeah.
What you saw is that you have occasional packet losses. They are not that annoying actually when you run, but they are still, I believe, they are still too much for being used in a sort of a real commercial deployment. And preferably we want 0 packet loss, especially with video. But as it is now, if I remember correctly, it was like 0.5% packet loss, which is a bit too high for video. And possibly one can use retransmission to cover it up, but then you add end-to-end latency also. So forward correction is not an option because the packet losses come in burst. It could be a burst of 10 packets lost, and that is can be difficult to forward correct unless you use interleaving or something like that. But get more complicated as packet losses come in burst, and that is also an indication that it's a tail drop queue somewhere, because there is no other traffic in the uplink. Was that an answer enough for?
Sure, maybe a quick question. So when you're saying that the packet loss ratio is low, only 0.5, that's kind of averaging over the entire session, or is it sort of locally? Because if you're saying that forward error correction doesn't work, it seems to be indicating that the instantaneous packet loss ratio can be too high for FEC to cover.
Yeah, in this case, it can be. Yeah.
Yeah. Mm-hmm.
We're trying to get in contact with the chipset vendors actually to see if they can resolve this issue, because it shouldn't be packet losses. It's outside the LTE specification, because the barriers that are used, the QCI9 barriers, they are sort of default barriers, and they use acknowledged mode transport in uplink. You shouldn't get any packet losses, but still you get them. So it's an implementation issue.
Jonathan, was it actually LTE the whole time, or did you said you were in a basement part of the time? Did you drop down to maybe an older specification as you were?
In some cases, you have less packet loss.
Yeah. No,
in some cases, you have more.
Were you definitely on LTE the whole time, or did you go down to 3G or something in poor coverage scenarios?
It's in good coverage also. Okay. So it's not really a matter of coverage. So I try to sort of study the issue and wasted a lot of hours trying to track it down.
You could still get loss in the queue, right? So this is where the loss happens, I guess.
Yeah, there is some queue somewhere that drops packets. That is what we believe. It's a bit hard to track what the issues are.
Jahed, I think the bottom line here is like the uplink is not optimized for this kind of thing. I mean, we're running like 30 megabit per second on uplink video. This isn't even like never been thought of.
Yeah.
When they're making the product, I think it's a specification perhaps. In production, I don't think like they have. And I think Ingmar didn't mention like we tried multiple vendors, multiple modems, and they all have same problem. So this is, I personally don't think like any condition control can solve that. So there will be packet losses until the implementation is done. So as Ingmar mentioned, like we're talking with some of the chipset vendor and see like if we can solve the problem, and that would be really good to see. But yeah, the uplink is for LTE or any RAT technology, radio technologies, there is an asynchronous system in downlink and uplink is not optimized.
Yeah.
And we're trying to get every bit of it. And I must say, like this scrim with my expectation was far like, well, we need to do a lot of tuning to do that, but Ingmar tells me that's not the case, and I'm really happy to hear that we can use in such as like really high demanding cases scrim. And thank you.
Yeah, I believe I'm also joking that that LTE is currently optimized for in the uplink. It's optimized for the transmitting pictures of your cats or flowers or flute or your kids or whatever. And, has not been on the table earlier, but hopefully it will.
Okay, Georgie?
Oh, sure. So actually, maybe I didn't clarify my question. So I was more interested in when you mentioned that like there are places where the throughput drops and then the congestion window doesn't back off in time. Presumably that would introduce self-induced losses, right? So I understand that the uplink sort of has some, let's say, non-congestion induced losses mysterious throughout, but I'm more interested in maybe the understanding of whether there's any places where it's a kind of a self-induced losses due to congestion. Yeah.
Yeah, of course, you get more packet losses, for instance, at 360 seconds. That's correct.
Sure. So maybe the feedback is that having a packet loss ratio trace graph would also be helpful. Yeah.
Yeah, that would, of course, have been. The thing is that I turned off the packet loss reaction because with the packet loss reaction, we only got like 2 or 3 megabit per second. And that is because you have sort of these packet losses are not really congestion related, but they sort of just occur.
Sure, you can tune your algorithm to ignore losses, but it's a different thing to say in the evaluation to still report on the kind of the loss trace. Yeah, that would be very revealing. Yeah. But by the way, it's a very cool use case. I think it's much cooler than making boring conferencing videos work better. So yeah, I really like that. Thank you.
At least the students had a lot of fun with it. So yeah. No, you can look at it yourself and have a private laugh. I can. Where were we? Maybe need to speed up or.
Sure. So just follow up quickly on Churching's point. I mean, there was the discussion of BBR in I think ICCRG earlier this week, and they got some strong feedback on ignoring packet loss non-congested.
Yeah, so I do that myself, and you shouldn't do that. I say it for the record: don't ignore packet losses. But in this particular case, I needed to do it, to get things running. So, but it's not okay. Okay, as a kind of conclusion, that you can get a high quality video with video feedback for a remote control applications by using congestion control. You're always getting black screens and long delays and that stuff, and it follows the channel quite good. And it was I expected worse behavior, especially when you're running in the basement, where you have really poor coverage, and even with the complex video recorder that we are using, and they are not really adapted for real-time application. They are adapted for surveillance, and still it works quite well. And you get good quality. I don't need to spend more time on. How much time do you have? Do you have time for extras or?
We have 15 minutes left, and we have the design team
time
report as well.
Go ahead.
So I think it's good if we can wrap up.
Yeah.
Okay. Thank you very much, Ingmar. Very interesting to see working in production.
So before I start, I'd say don't ignore the packet loss, but use something called ECN to actually solve the problem. Not try too hard on your congestion control algorithm to solve all packet loss issues. That would be my message. So here, my name is Jahid Jamasharkar, and I'm going to represent the RMCAT design team today. So the RMCAT design team, I think those who have been following RMCAT knows we're trying to do some generic congestion feedback messages. So next slide. So what I'm going to do to tell you what we have been doing so far, and what is the current status and what's going to happen in AVD core. So after IETF 94, as far as if I'm correct, we the RMCAT group, working group, decided like, okay, let's analyze all the requirements from different proponents. We at least have 3 proponents at that time. The initial slide with 3 circles represents that one. So we have 3 candidates. They have different kind of requirements. The design team was formed so that, okay, you can look into the requirements and see like if we can basically find a generic feedback message. Then the design team have been working almost like 2 years now. Then they have been meeting and they have been producing different kind of analysis and results, and finally produced a design and presented as a 2 kind of format, Excel block and RTC feedback message. Then we presented this to FET core because RMCAT doesn't have the authority to finalize that kind of thing. It was not chartered to do that. So we went to FET core and said like, well, this is what we have. We have Excel block based and we have a RTC block based. And then we got some feedback, and I think the most decisive factor was the deployment possibility. So it was noted like people has more experience with RTCP kind of feedback, and they have like, you have feed, you have timber and all these things there. So it was saying, the comment was like, if we can drop the Excel block and focus on this RTCP feedback, so that get perhaps more deployable. So that's what happened. Next slide. So this is the goal. If you don't remember, this is a recap again. As I said, the design team was formed to analyze the requirements of the candidate algorithms, and then try to say and generic feedback message. And I think one of the main reasons to do that is interoperability. So basically, one application that implemented, say, GCC, and they want to talk with Scream or NADA in a communication, point-to-point communication or whatever, they should be able to talk to each other. So not everybody need to implement all of them, because we had in a situation like, I don't think like RMCAT in a situation right now that say like, well, for at least experimental purpose, we'll have 3 candidates up there. So this was one of the things that, okay, if we have a common feedback message, then we solve a lot of issues. So next slide. So the design team have been looking into the different requirements. So one of the things like, okay, we need a packet level kind of information. And also there was a consensus in this group, RMCAT, saying like, we'll go for a sender-based adaptation, because there was like some of the algorithms were like receiver-based, some of the algorithm was sender-based. I think Scream was sender-based from day one. Then GCC came and also became a sender-based or hybrid kind of. And NADA has been doing receiver-based, but they also said like a sender-based might be really good. And the reason for sender-based was basically more manageability and deployability again. So these are the then design team. When we looked into that one, design team kind of have 3 kind of information that's important. One is a packet identifier. That's the RTP sequence number. You basically see like you can calculate loss on top with that. Then you have packet arrival time. That's important. You would like to, one of the big input to our algorithm design have been the delay and jitters. And obviously, you would like to use ECN if this is used. So basically, if your path is supporting ECN, you have ECN mark big, you would like to also convey that back. So these are the information we said like, well, we all agreed on like, these are the information we need. And the next phase is to have the packet format, right? Yeah, so we also said like, well, this will be information and this will be sent by group by SSRC. So next slide. So as I said, like now we have only one packet format, where packet format that's done based on like RTCP transport layer feedback messages, and this looks like this. I think I don't need to tell you like there are some header here, like on the top of and the bottom, like RTCP report timestamp. That's the thing coming up with header. If you, I think it's 4585 says that. And then we have for this feedback message, we have like beginning sequence, end sequence. For one kind of SSRC, when you're reporting it, you have a beginning and end sequence. and that's like the number of packets you are reporting and per basically report block. Then you have L bit saying like whether this packet has been lost or not. If it is lost, the ECN field and this arrival time offset all gets zeros. And then basically ECN, obviously, as I said, like we need to send back the information whether the packet was ECN experienced or not. And then also you have a arrival time offset, and this offset is calculated from the reporting timestamp. So basically, when you generate report, you kind of put how do you call it in English, in behind, or how on past you have received the packet. Yes. So this is like currently how it looks like, and obviously as I think the suggestion packet type was like 205. That's like transport layer feedback message, right? So with this, we also thought about like, okay, the different candidates also had different. I mean, they tend to send in this interval report in different interval, and when we analyzed their proposals, it was between 50 to 200 milliseconds. And the decision of the design team was like, okay, you negotiate the interval. Either you have some default interval, and then you can negotiate between these two. And there was, I think Colin did some analysis, and it was shown like you can do even like per frame feedback, per media frame, you can have a feedback generated for a certain use cases, right? So this is how it looks like right now. Next slide then. So the current status is like this. I think Chairs already said like now this design team draft has been replaced by AVT Core. AVT Core working group will be taking the CCFB. That's the new kind of name. Maybe you would like to use like Timber or something, CCFB. Yeah, that's something new. So the AVT Core will take this draft and make it finalized through the standard process. And the expected count is like you have a standard RFC out of it. So this is the current status. And next slide. So what happens to the RMCAT design team? I think this is up to the working group. But from as a RMCAT design team lead, I would say like job well done. We have done it for the we have this. That's why I put the goal there. Like what we are supposed to do. And to me, the draft looks really good. There are some, I think there are some editorial changes needed. Like there are lots of places we use the term design team and all these things. So that need to be changed. But I don't think there will be too much fundamental changes in the information required or the packet format. And obviously you can say like there are like during this process of this packet selection of packet format, we have been analyzing different like, well, run and RLE for like lost packets. Put ECN marks in a separate vector so that you don't need to send it every kind of report blocks and stuff like that. I mean, all those optimization could be done, and we can revisit all those things. But the basic information needed for a sender-based algorithm to work, that is kind of fixed. The packet format can always, you can shift here and one bit here and there, but I don't think like you need a design team to do all those things. So I think we can just conclude the design team, and on our AVT Core we take the comments as it is. My proposal would be like everybody follow this work in AVT Core, and maybe our authors of this draft, we can sometime, if there is a major change happen or any progress happens in AVT Core, we can come back and give an update of that one. But I don't think like for all those things you need a design team. But that's what I say. Think.
Yeah. Jonathan Lennox as AVT Core chair. I mean, the two things are certainly when we do working group last call in AVT Core, we'll make sure to notify RMCAT to say, please review this and comment on AVT Core.
Yeah.
And then the other thing is if the document authors choose to keep using the same methodology they've used with the design team, that seems to have been quite successful. So I'd be happy if they did that. But it's the same people in a, with the different, hats on. But that's fine.
Sure.
Ingemar Johansson. I read the draft on it recently. I've unfortunately ignored it before. Sorry for that. And I believe it seems to be doable to implement it. And I will actually, when it turns out that it's deemed mature enough, I will sort of implement it. That instead of this botched version that currently implemented. But maybe one comment that needs to be refined is that it's a feedback per frame that will, at least in high bit rate, that will cause Scream to hiccup, because the keyframes can be horrendously large. And if you went for entire keyframe, you know, to send a feedback frame, because of delays in the network, you can spoil the hack clocking. It will probably not hit the other algorithms, but the Scream will suffer from it.
But so. I think you here the idea is like, no, you're not supposed to like that's the target, like per frame. But obviously you can actually do the range report. So you can select like I think the amount of time is.
So I mean, you can configure your RTCP
exactly
to whatever you like. So if you need feedback more often, just configure yourself more RTCP bandwidth, and then you can report more often.
Yes.
And also when we say per frame, we mean set the interval of which you send the feedback packets to the reciprocal of your average frame rate, not actually wait till the new frame arrives.
Maybe also maybe you don't need actually per packet feedback, perhaps, even if it's a big iframe chopping up into a different number of packets. So with that, I don't have anything to say actually, and I would like to thank all the design team members for doing this. It has been a really good experience.
Yes, thank you to the design team. Very good, and I think it's nice if you when you submit the new versions, you can also inform on the RMCAT mailing list that there is a new version, so that people are still aware. And then they can follow it in the AVT core discussions. Yeah. Okay, thank you. That is the last item on our agenda. So unless anyone has any other comments, we can conclude for today. So thank you all for coming.
Thank you. Bye-bye.
Thank you. And if we could get the blue sheets, please.
So, actually, maybe we can discuss this. I was just reading this. Of course, I did actually specify what
And if you did not sign, please come up and sign.